All right, let's take a look at our lesson for today. Today we're going to talk about definite integration. Up until now we have been talking about indefinite integration. So let's look at the differences. If you would look at this picture right here. So this, just some vocab words. This is our integrand. We've talked about that before. This tells us which variable to integrate. The integral sign, we've talked about that before, but today we're going to be looking at these two additions to our integral. Those are the upper and lower limits of integration. So that's a definite integral. You can tell the difference between them because a definite integral will have numbers on the integral sign and an indefinite integral won't. So that's the difference. And what they basically do for us, a definite integral, we'll be able to calculate the area under the curve. That's one of its uses, is calculating the area under the curve. This is a picture right here. If I have the integral from a to b of f of x dx, what it's doing, if this is f of x right here, what this integral will do for us is it will calculate all the area under this curve from a to b. So all this in here we will be able to find if we could do that integral. All right. So there are a couple of different rules. You know, we kind of only had two rules for integrals. It's just two. But when we're working with definite integrals, we have a few more that we can look at. One is the order of integration. So let's say, for instance, that we have a b and an a here. You know, a lot of students like to integrate that this is the smallest number and this is the biggest number. You know, do you have to do that? No. You can integrate the other way. But let's say you wanted to change the bounds, or you wanted to switch them, you wanted them to switch places. You are allowed to do that, but you just have to take the opposite of everything. You would have to do a subtraction out front. So that's a rule. We also have the zero width interval rule. So, you know, so this is from a to a. If we integrate from a to a, let's say we're going to find the area under the curve from 5 to 5. Well, there's no space, right? It's from 5, starts at 5, ends at 5. There's nothing there. So that is the zero width interval, and that yields 0. There's no area that would be. They like to play with these kind of things and, you know, maybe make a really hard problem to integrate, and then the bounds are like 2 to 2. You know, it basically just means, oh, that's 0. We have our faithful little constant multiple rule that works with indefinite integration as well, where we're allowed to take the constant and pull it on the outside. We have our sum and difference rule, which also works with indefinite integrals, where if we're adding or subtracting the g of x, f of x, we are allowed to integrate them separately. This last one, the additivity, this is one that just applies to definite integrals. And for me, I have to kind of draw this out. So I have a, and then b, and then c. Okay, so what this is telling us is, if I take the integral from a to b, so let's say there's a curve up here, you know, some kind of a function. Let's say if I take this integral and I calculate, let's just calculate the area under the curve right there from a to b, and I add to that this one, I calculate that one, then what this rule tells me is that if I take that first one and calculate it, then add the second one to it, that's the same thing as if I took the whole thing from a to c, if I just integrated this whole thing. And that allows us a little bit of flexibility. There are some times when we want to split an integral, there'll be cases where we really have to. So that just gives us the freedom to be able to do that. The other thing that I want to talk about before we get to our even and odd stuff. So let's talk about the theorem as soon as the board clears. The existence, there we go. So for definite integrals, what this is telling us is that the function has to be continuous over the interval that we are integrating from, a to b. So for AB calculus, we just basically if we see one that's not continuous on that interval, we just kind of say, well, we can't do that. You know, that's undefined, we can't do that. For BC calculus, we will learn in Cal 2 there is a way to integrate functions over discontinuities, but there's a special technique that we'll learn, and that we'll learn, you know, later, like in January, we'll learn how to do that. But for now, we need to understand that in order for this definite integral to work, the function needs to be continuous over the whole interval. All right. So we have a couple of special cases here that I want to talk about before I get to the technique we're going to be looking at today, which is using geometric shapes to calculate integrals. And one is, well, we're just going to look at even and odd, and these are special cases. I have seen multiple choice questions that involve these kind of special cases, so just want us to become familiar with them and make sure we understand how they work. So if a function is even, then it has y-axis symmetry. So an example of that would be like the parent parabola, y equals x squared. That's an even function. And what this tells us is, it tells us that if we integrate from negative a to a, notice how it's a. It has to be like negative 2 to 2 or negative 5 to 5. That's the only time this rule works, is if the integral is like that, from like negative 1 to 1. If that's true, if we integrate from negative a to a of this even function, that is the same thing as multiplying 2 times half of it, you know, from 0 to a of f of x dx. That kind of makes sense since this is symmetrical, that we could rewrite it that way. Instead of doing this entire piece, you know, let's say this is negative a and that's a. Instead of integrating that whole thing, if we just do half of it and double it, then that's helpful. Now right now you may not understand why it's helpful to have a 0 on a bound, but that's actually kind of nice if we can do that. You'll learn that actually tomorrow. Alright, so that's our scenario. Let's look at some problems that involve even, when f of x is even. So we're given this piece of information. We're told that f of x is even, and we're told that the integral from 0 to 5 of f of x is 3. Okay, so let's see what they want us to do. They tell us from negative 5 to 5 of f of x dx, so they want us to find that. Well, what we can do is we can use this rule that we just learned, and we can say that that's the same thing as 2 times the integral from 0 to 5 of f of x dx, which is going to be 2 times 3 or 6. Now for my students that like to conserve energy, it's probably a little upsetting that we're having to write all this down when the answer is 6. But that's what we need to do. We need to show the calculus of how we know the answer is 6. So we write out that integral. On the second problem right here, they want us to find out what the integral from negative 5 to 0 is. Well, since it's even, we know that this integral is going to be the same as the integral from 0 to 5 of f of x dx. They're going to be the same. And that integral, we already know right here, is 3. Okay, and our last one, we have this fun rule. You know, we don't have that many of them. Let's take that constant, let's pull it outside. So it's 4 times the integral from negative 5 to 5 of f of x dx. So we just actually did that one up here. That would be 4 times this integral 2 integral 0 to 5 f of x dx. And so that's going to be 4 times 6 or 24. So that's our work with even, just kind of a special case, only works on even functions that are integrated from negative a to a. So we also have a special case with odd functions. And on this odd function, what we have is, you know, an example of that would be our x cubed, y equals x cubed. That's an odd function. And so in order to understand this one, we're going to have to talk about the sign of area. So we know, you know, area can't be negative. I mean, area is a thing, right? Like distance can't be negative. But what I like to do is think about You know how velocity can be positive or negative because of a direction? I like to think about area that way. It's like a direction. Like if area is under the x-axis, it has a negative sign. And if it's above the x-axis, it has a positive sign. That's just the way area works. So let's look at this particular case. If we have an odd function and we're going from negative a to a, basically what we have going on is, so let's talk a little bit more about area under the curve. So I'm looking at the area between the curve and the x-axis. So that's this area right here, between the curve and the x-axis. Okay, so if my drawing was great, which it's not, but if it was great, we would see that those areas are equivalent. They're the same. And so if I have the same amount of area above the x-axis as below the x-axis, it nets out to be 0. So that's basically it. If you have the integral from negative a to a of an odd function, the answer is 0. That's what you get. So let's look at an example that uses that. All right. So we have given f of x is odd, and we're told this little piece of information that from 0 to 5 f of x is 3. So let's interpret that. So if I go from negative 5 to 5, well, that's the rule. That's 0. There's really nothing to write. I mean, that's just this rule right here. It's 0. Okay, so now let's think about this. So I know from 0 to 5 it's 3. What do you think about from negative 5 to 0? What would that look like? Yeah, that would be negative. So that's going to be negative 3. Okay, oops. That's a negative 3. So the last one, all right, let's pull the 4 out. We get to do our rule, yay! From negative 5 to 5 of f of x dx. We already know that, okay, so 4, we know that that's an even, so, excuse me, it's odd. So that's going to be 0, and 4 times 0 is 0. So that's just a little bit of a side note on even and odd. And again, it only works if you're going from negative a to a, like negative 2 to 2, negative 5 to 5. Those numbers have to match. All right, so let's look at the other part of our lesson, which has to do with an integration technique that we're going to work with. So if you recall, when we first started integrating, I said you really should keep a list of integration techniques, just a list that we could look through, that we could work with. And so we're adding a third one to it. If you would turn to that. Our first integration technique, if you recall, was formulas, using a formula. So we learned that on the first day. How do we use a formula? The second technique that we learned was U sub. So we have learned how to do U sub. Okay? So we're going to be working with the third technique today, and this technique actually only works with definite integrals, but this is geometric shapes. And we really like this technique, geometric shapes. If we can find the area of a geometric shape, that's way easier than finding the area of, under a curve. It's just easier. So we're going to learn that first. So let's start with our first example. We are integrating. Now this is with respect to x. We're going to go from 1 to 6. Those are our bounds. This right here means y equals 4. So we're going to be at 4, and we're going to draw a shape. So we're going to be at 4, it's this line right here, and we're only going from 1 to 6. So what that makes us is a rectangle. That's a rectangle. And even when you learn to do fundamental theorem of calculus, which we are going to learn tomorrow, thinking about it as a geometric shape is way easier than working through the fundamental theorems. So it's just kind of a little shortcut for us. This distance right here would be 5. And this distance is 4, so 5 times 4 is 20. So our answer to that integral is 20. All right, great. Let's go to the next one. So on this one, we're integrating from 1 to 3, and that's a line. X plus 2 is a line. So I'm really only interested in the line between 1 and 3. You certainly can draw the whole line if you want to, but I really only care about that small little part. So what I normally do is I would put a 1 in here for x, and that would give me a 3. So there would be a point. And then I would put a 3, this 3 in here for x, and that would give me a 5. And that would give me this point. And so I have a trapezoid that I need to find the area of. Alright, so let's do that. So it's 1/2. Base 1, this is my first base, and that's 3 plus base 2, this is my second base, and that's 5. And then the height is this part right here. The distance between those two x values is my height, which happens to be a 2. So then we have, what, 8, half of 8 is 4, and 4 times 2 is 8. So that is our area for that. That's our answer. That's the area under the curve. This third one, this one usually drives students a little bit crazy. It's kind of hard to recognize what kind of geometric figure is that. Now we really would prefer to work it as a geometric figure. I will tell you that we will be learning some cool stuff, like we're going to learn trig substitution. That's a great integration technique. That sounds so fun, doesn't it? Trig substitution. We're going to learn that, and we could actually do this integral with trig substitution. Now it is super fun, but it takes a little while. So if instead we could recognize that that is an actual geometric figure, it would just make our work go faster. So hopefully you've recognized what it is. I'll go ahead and write up here. Maybe it'll be more clear. We certainly recognize what that is, right? That's a circle centered at the origin. If I solved for y, I would get plus minus radical 4 minus x squared, right? So what this is the top half of a circle. It's basically the top half from -2 to 2. The positive sign, if you recall, goes when y is positive. When y is positive, it would be this piece right here. If we were looking at the negative one, that would be when y was negative. That would be this piece down here. Okay, and that would give us our whole circle. But we're just looking at, this one is just the positive piece. So we're looking at this piece right here. And we happen to be going from -2 to 2. That's kind of handy because that's the radius, right? The radius is 2. So that's actually really handy. So we can just use our formula for area of a circle. We'll do half, and then our pi r squared. R happens to be 2. So basically we've got, what, 4 times a half? So our answer would be 2 pi. That's the measurement of the area under the curve. All right, great. So this picture right here, this is a classic kind of problem that we typically will see. It'll have lines and sometimes semicircles or quarter circles, and they'll ask us to do all kinds of different integrals of a picture like this. So we're basically going to go from -4 to 4. So -4 to 4. And what we need to keep in mind is that we measure, the integral calculates the area between the curve and the x-axis. So it's going to calculate this part right here. We're going to actually have to calculate that, right, between the curve and the x-axis. Right here, it's also underneath the x-axis. It's going to be negative, which is why I'm coloring it red. So above the x-axis, this part right here is going to be positive. And our job is going to be basically to find the area of those 3 triangles and add them together. That's what we are going to do to find this integral. We're integrating. We're finding the area under the curve. So this one is what, 1/2, let's see, base is 3 and height is 2. So that gives me, what, -3. So I have -3 plus. So now let's work on this one. So 1/2, base is 3 and height is 3. That's 9/2. And then this last one, 1/2, base is 2 and height is 1. What is that? 1 minus 1. So we use our arithmetic and we add all that together and we get 1/2. So that integral is 1/2. Okay? All right, so this problem, we'll see some like this too, where we're just given some random information and asked to generate other integrals. So this goes from 0 to 3 and 3 to 0. So I'm going to, draw my little picture because that's what I have to do. So 0 to 3 and 3 to 7. So from 0 to 3, that's an area of 4 on whatever curve is there. From 3 to 7, that's an area of -1. That's just going to help me kind of understand what they're asking for. All right. So the first one, they ask us the integral from 5 to 5 of f of x. Well, we're like, 5? We don't have anything about 5's up there. But then we think, oh, wait a minute. That's 5 to 5. That's my 0 width interval, so that's just 0. Okay, great. That was easy. All right, so the next one wants 0 to 7. So this whole space, I know we can visually see that's going to be 3, but of course just writing answers down is not adequate. We're going to have to, show the calculus behind it. So the reason that we know that that's 3 is we would split this integral into two pieces. We would integrate from 0 to 3 of f of x dx plus the integral of 3 to 7 of f of x dx. So the integral from 0 to 3, we already know that's a 4, plus the integral from 3 to 7, we know that's a -1. So our final answer would be a 3. Great. Okay, our last one, we want to do basically the integral from 3 to 7 of 2 f of x dx. Okay, great. We get to use our, our little rule. We don't have many of them, so we're really happy when we get to use one. Let's pull the 2 out. 3 to 7 of f of x dx. So that's going to be 2 times, and what did we say our integral from 3 to 7? That was -1, so it gives me -2. All right. Okay, for our last problem, I saved the most fun problem for last. All right, so this one is with respect to y. Okay. So that means that these are y bounds. These are not x bounds. They are y bounds. We really are not used to graphing with respect to y. We're just not. And for years, we've been graphing for years, and we've only been graphing with respect to x. So it kind of freaks students out sometimes when they have to graph with respect to y. Now, it's really important that you kind of embrace it. Just embrace the graphing with respect to y, because soon, the next unit, we're going to be doing area and volume, and a lot of that's going to be with respect to y. I encourage you not to try to find tricks like turning your paper or doing things like that. Let's just not do that. Let's just leave it as y's, just like it is. So this equation basically would be x equals y minus 1. That's the equation. So now let's graph it. It's a line. You can certainly think about it as y equals x plus 1 if you want to, but we're going to go from 1 to 4. Okay, we have y bounds, and we're going to, like what I did up here with this line, I plugged the 1 in and I got, a 3, and I plugged the 3 in and I got a 5. I'm going to do the same thing here, but I'm going to plug a 1 in, and that gives me a 0, so x would be 0. And then I'm going to plug a 4 in, and 4 minus 1 is 3. That means x would be 3. And that's what we're looking at. Okay, that's the curve. Now, really important here. We are with respect to y. So this axis that has been, like, wow, we just love the x-axis like our best friend, right? Wow, we love the x-axis. Doesn't really matter anymore. It's all about the y-axis when we're with respect to y, all about the y-axis. So I'm looking for the area from the curve to the y-axis. That's what I'm looking for. I am not looking for the area from the curve to the x-axis, because this is with respect to y. And I think you can see that these are different areas. This area would be like the area of a trapezoid, and this one is a triangle. So it's really important that we get straight. When we are integrating with respect to y, y is the important axis, and we're measuring from the y-axis out to the curve. That's the kind of area we're looking for right there, that triangle. So now that we have it drawn correctly, it's just a triangle. So it's 1/2, let's see, our base would be, 3, and height is 1 to 4 would be 3. So that would give us an area of 9/2. All right, great. That was super fun, wasn't it? All right. All right, hopefully we're all good. Okay.